Hey everyone, I'm Sunny. I've built code systems and engineering teams at places like Atlassian, Geostar, and now Metaforms. Uh, I've built for real scale, and you know, products that I've built have gone on to break world records. I'm also the founder of Team Siksha, and this is my initiative to start a recorded series of learning computer science from first principles. This is for anybody looking to familiarize themselves with uh, how modern technology works. For example, when you use an app, uh, either on your mobile or on your laptop, uh, what happens behind the scenes, right? Eventually, when you become developers, these days, most of us are using AI to generate code. It is always helpful to understand how these apps work under the hood. One thing that I have realized over the past 15 years is that people who understand the basics well tend to do so much better than those who don't. And I myself have had a lot of success when it comes to trying to learn things from first principles. This is also a way for me to stay abreast with the industry and also try and relook at all the concepts I may have lost along the way. So let's get started. You know what? Every time you open an app, either if you're sending a message, you're watching a video, or you load a website, something remarkable is happening. Your device is storing information, converting it into bits, transferring those bits across networks, and then finding another computer somewhere in the world and interpreting the response. I mean, there's so much happening here. The other computer may be a mobile device itself because modern mobiles are yet another personal computing devices. The six questions that we rarely stop to ask. I mean, all of this works so smoothly that we rarely stop to ask, how does a computer remember anything? What happens to data when the power goes off? How does one computer send information to another? How do two machines agree on what that data means? Why do we even need protocols? And how did all of this evolve from things like human language, telephones, telegraphs, and maybe cards? How did we go from there till the internet? In this video, we will build the story from first principles. We will begin with the most basic question. How can a machine represent information? Then we will move through memory, storage, communication, protocols, computer networks, and finally the internet. By the end, when you open a website or call an API in the future, you should have a much clearer picture of what is happening underneath. Let's start with part one. Humans are social animals. Everything begins with communication. So humans have always had the need to communicate, right? We communicate for various things. We want to talk about, let's say, sharing food, warn each other about danger, to coordinate work, to preserve knowledge, to tell stories, and also to build relationships. At the beginning, communication was local. So, you had to be in front of the person or near a person who you wanted to communicate with, right? So at that point, we could use gestures, facial expressions, sounds, spoken language, drawings, symbols, written language, right? Language solved an important problem. We were able to do so much more. We created spoken language. We eventually started using drawings and symbols as well. Symbols eventually helped us communicate. So I could write something down and pass it over to future generations. Eventually, these symbols and drawings translated into written language. Now, all of this is exciting because computers are no different. For example, if I say the word water, the sound itself is not water. It's just a set of sound coming together and giving it a meaning. You and I both understand water to mean the same thing, right? And so it's a shared symbol that points to a concept. This is the first important idea. Communication requires shared meaning. So as long as two parties have a shared understanding of symbols or sound in case of humans, you can communicate. If I use a word that you do not understand, the sound may reach you, but the message would have failed. The same principle applies to computers. A computer may receive a sequence of bits, but unless it knows how to interpret those bits, communication is useless. Hope that makes sense. Communication at its core has three layers, right? A useful way to think about communication is to separate it into three questions. One, what are we trying to say? Two, how will we represent it? And three, how will we transport it? What are we trying to say in the previous example was I trying to say water, right? How would I have represented it? I was going to use sound, so I said water, right? And how was it to be transported? Transport can happen across multiple mediums. In this case, when I am saying water, air waves are transferring this sound to the other party, and then they are able to either decipher it or be confused. Suppose I want to send the message, meet me at 5 p.m. This could be represented in multiple manners, right? You could either use spoken English, which is, for example, as you say things. You could use written English. You could write this down. You could use Morse code. Standard Morse code is a way of communication used across long distances, and it uses dots and dashes to encrypt information, right? You could use Morse code. You could send out a text message, or you could literally sequence this message as bytes, right? We'll get to the sequence of bytes eventually, but spoken English is transported through air. Written English would be ink on paper. Morse code can travel via electrical signals. Text message from your mobile actually can also use radio waves. Yes, it can also travel across electric signals. It's a combination of both. And sequence of bytes, if combined well together, can become packets on the internet. And that is what we are here today to unpack. So over the course of today's session, we will understand how packets on the internet are actually just sequence of bytes and how they reach the right places. At its core, what is data? Data is a representation, right? I mean, the number 5 here uh, could be represented in multiple forms, right? I could speak 5. I could write 5 as the symbol itself. Romans used to write something like a V to represent 5. In binary, it is represented as 101. Electric signals could actually be a turn on the electric signal, turn it off, and turn it back on again to then say, hey, this is 101, right? You could literally just say magnetic patterns of ones and zeros to then represent the same things. So let's meet the bit. In case of computers need representations that their electronic and mechanical components can reliably handle. The simplest useful choice is to have one state or the other. For example, current or no current, high voltage or low voltage. Either it is magnetized in one way or the other. We call these two states bits. A bit can have one of two values, 0 or 1. The word binary simply means that we are using two possible states. And so the next obvious question is, why use two states, right? I mean, why not use 10 states, for example? Uh, Computers use binary because physical components can reliably distinguish between two states. It is really difficult to build a physical system that perfectly distinguishes 10 different voltage levels under all conditions. I mean, it's much easier to distinguish either the voltage is present or absent, if there is a light or there is no light, if there is a magnetization in one direction or the opposite. If I was to try and look at 10 different values of voltage, think about the case where there's going to be a value between 7 and 6. I mean, is this 7 or 6? You want a huge margin for error when you have two states. So even if you choose 1 to be voltage present and 0 to be voltage absent, even if there is a slight voltage, you know that you can assume it is 0. And even if voltage fluctuates a bit and it goes down by a very small amount, you know that the value still is 1. So assuming we go ahead with bits, what can a bit represent, right? I mean, one bit can only represent two possibilities, 2 to the power 1, right? I mean, 2, either it's on or it's off. When you increase the available bits for representing information, suddenly you start seeing that the amount of data you can fit in per set of bits increases, right? So 2 bits represent 4 possibilities. 2 to the power 2 is 4. And so you could have values like 0, 0, 0, 1, 1, 0, and 1, 1. There are 4 values now just out of 2 bits. And so when you go over to things like 8 bits, we are looking at 256 possibilities. Just with 8 bits, we are able to come up with 256 unique possible values, right? 8 bits together is called a byte. This is enough for a character, a small number, or a color channel in itself. What it means is, if you wanted to store characters, you could store a character in 1 byte. How many unique characters do you have? You have almost 26 characters. Take lowercase, uppercase, take 9 different digits, right? Even if you wanted to store colors, you can store colors also as part of the same 8 bits or a byte. Text is also data. Computers do not inherently understand the letter A, right? So they store the number in a convention that maps to the letter A. For example, water does not actually mean water, right? It's just you and I understand water to mean the same thing. Essentially, computers also have a convention map that they use. One of the standards used is called ASCII, ASCII. This is a shared context, and many companies, many eventually, standardized on this one. And so, most modern computers understand ASCII as a convention as well. A in ASCII is represented by the number 65. So, if you were to represent a binary of 0, 1, 0, 0, 0, 0, 0, 1, it would actually translate to the decimal number 65, and that is the equivalent of the character A. The binary pattern can be transmitted as an electrical or radio signal as well now, right? Because now you could be sending signals like 1, 0, 0, 0, 0, 0, 1. And so when you did this, this is exactly when you were able to represent the same binary format as an electrical signal. Similarly, on the receiver side, if I was to receive this binary signal and translate it into my zeros and ones, I can then internally represent and understand, hey, if I have received the ASCII value 65, I know by convention that we are talking about the character A. Eventually, we went on to support Unicode, which allowed you to represent even more characters. For example, these are various other characters, including emojis. All of that can now be represented using a unified code or a unified convention, which is now called Unicode. At the core, anything that you do inside a computer has to be represented as numbers. I mean, there's no other way. Even if you're looking at an image, even if you're hearing some sound, or if you're watching a video, everything at its core is represented as numbers, and those numbers are eventually converted to binaries, right? What you're now doing is you're translating every pixel into a set of numbers, and those numbers are then represented as binary. Likewise, for audio, this is just modulations, and so they are also essentially just numbers. Videos are effectively images played as frames per second, and so because every image can be saved as binary, a video can, at its core, also be just saved as binary, right? I mean, there are multiple other things that happen when it comes to videos. Eventually, in some following videos, when we get into the basics of OTT, we will talk about various ways of encoding videos, and you'll understand that it's not just stitching multiple images together that would lead to a very high storage requirement, but that's for a later video. At the bottom, all of it is just bits, right? I mean, hopefully this is now making sense. Let's now look at how machines are able to remember things. Charles Babbage designed the analytical engine in the 19th century. It was never completed as a fully functioning general purpose computer, but it included ideas such as memory, computation, and punched card programming. Punched cards became an important way to represent instructions and data. A card could contain holes in particular positions. So for example, if you see here, so this is the punch card. Let's take a closer look at punch cards. The presence or absence of a hole represents a state here. In a simple interpretation, a hole means 1, which is very counterintuitive, but a hole in the punch card actually means 1, and if there is no hole, it means 0. A standard punch card could have 80 columns, 12 rows, and 1 character per column. Let's say in this entire column, depending upon the value, you could then say, hey, the representation is 0, 0, 0, 0, 0, 0, 1, 0. And so that literally stands for binary of 2. And so 1, 0 is what this means. Punched cards were actually used in data processing long before personal computers. I mean, before the computers that you and I use today. It was used in data processing by Herman, famously for processing information from the 1890 census. If you were to get this done by hand, it would have taken years of counting, but by machine, it was done within a fraction of time. And so that is where eventually humans started realizing they needed some of these mechanical ways of being able to process information. In fact, the company that actually grew from this eventually became what you and I today know as IBM. The cards had obviously a lot of advantages, right? They were cheap, they were easy to duplicate, They did not require electricity to retain information, and they could be physically sorted and transported. But then again, I mean, with papers, there were definitely some serious limitations. And so they occupied a lot of physical space, right? Reading and writing was slow. A damaged card could cause errors. Updating information was inconvenient, and programs had to be represented as physical card sequences. A punched card deck was, in a sense, an early external database and a program file. If you look at it, this representation effectively is just a database. At that point, if you wanted to store a bunch of data, you would punch them into cards, stack them together, store it somewhere, and whenever you wanted to read, you could bring it out and start reading through it. It would have been slow, no doubt. Eventually, we did come up with something very interesting, and this is not something I had explored. So during research, I found out about this. They created something called as a paper tape. It was the same idea. Rather than having cards and stacking them together, you could literally just roll out this tape in this reel sort of a thing. And instead of a single card, this continuous strip of paper would contain holes arranged in rows. Paper tape was used to store machine instructions, text, telegraph messages, or configuration data. It could be read sequentially, similar to reading a long stream from beginning to end. It was very interesting, and you could only read in sequence. So even if you wanted to stop reading at some point, you would still have to pass through that same set of data to then arrive at the data that you wanted to probably resume at. This brings us to a very interesting concept. Uh, Even today, sequential access and random access are very important concepts, and when we get into system design eventually, but sequential access reads data in order from the beginning. Random access can directly jump to any particular location. A cassette tape, for example, I don't know how many of you all know about cassette tapes. So in case you had a Walkman or a audio cassette player, these cassettes would have reels and you would have to go over in a sequential manner. Even if you were fast forwarding, you were literally increasing the speed at which it was reading through, and then once you stopped, it would again resume wherever you stopped. A database index or a RAM address today, as it is used in modern computers, allows you to do random access. And when that became possible, it just allowed computers to get really, really, really fast. And we'll learn more about that in some time. So early electronic memory was very different, right? I mean, electricity did make computation fast, as we discussed. Electronic computers introduced a very different possibility. Instead of representing data with holes in paper, we could represent it with electrical states. This made computers much faster. A machine could hold data in circuits and manipulate it using logic gates. At first, this created a problem. If data was represented by electricity flowing through a circuit, what would happen when the electricity stopped? You would lose all the data, right? And this is where we saw that information would disappear. This is the origin of the distinction between volatile and non-volatile memory. So volatile memory is memory that is lost when the system restarts. Non-volatile memory is memory that can be modified, but it is not lost when the system restarts. Volatile memory requires power to retain its content. Modern DRAM, for example, one of the most popular volatile memories. Unfortunately, the prices have gone really crazy, but let's get back. Modern DRAM is a familiar example. A simplified DRAM cell stores bits as a electrical charge. The thing with electrical charges is that charges gradually leak away, and so the memory must be periodically refreshed. When power is removed, the contents disappear. This is why your running programs and unsaved changes are lost when a computer suddenly shuts down. RAM is very useful because it is fast, it is directly accessible, it is relatively simple for the processor to access, but it is not suitable as the only form of storage. RAM starts empty. The operating system must be loaded from persistent storage into RAM before the processor can run it. Non-volatile storage keeps its promises. The state does survive when power does not. Basically, to say non-volatile storage retains information even after power is removed. Some of the examples are punch cards, magnetic tapes, hard disks, CDs, optical discs, pen drives, as you may have used, SSDs, ROM. At the core, all of these devices remember the information that was stored inside of them when power is removed. Right? You could just plug out a USB drive, and when you plug it back in again, you can access the data once more. At its core, the history of computing can be viewed as a very long search for better trade-offs between a bunch of things. You want to get as much speed as possible, but you want to do it in as less cost as possible. You want to get as much capacity as possible. You want it to be super durable, which is to say, how long can uh, the data be retained. Then you want to use as low power as possible, and you want it to be as small as possible. And lastly, it has to be easy to access, right? If you notice, all of them are stretching your requirements in different directions. And so there is always this trade-off between so many of these concepts when it comes to building computers. And the history of computers is very interesting. We'll continue talking about that for a bit more. Let's talk about magnetic drums. Computing, in its earliest stages, tried to use the fact that magnetic materials remember their orientations. And so, one of the earliest things that we built was a magnetic drum. Obviously, there were many other things that came before that. Just picking up one of the items that you may or may not have come across. Given the fact that a magnetic material can be magnetized in different directions, we could use that direction to represent binary states, right? You could either be oriented north or you could be oriented in the south direction. And so if I was to then use a magnetic drum and have multiple cylinders coated with magnetic materials on the surface, I could literally have as many sectors on this magnetic drums, right? So for example, this is one sector. This is another sector. If I was to represent it like that, then one thing, if you notice, is I could orient this by turning it around, right, for it to reach here, and then this can read if the value is 1 or 0. And so you could actually, here it could be 1 0 1 1 1 0 1 1. You could use this to your advantage, and you could actually change the magnetic direction by applying electricity, or you could read the previous direction stored at that sector, and this way you were now able to switch the machine off if need be and still be able to retain data across multiple usages. Because the drum had to rotate to bring the required location under a read or a write head, access was slower than modern RAM. Still, magnetic storage introduced an important idea, the fact that data can survive after electricity is removed, because it is represented by a physical state and not a continuously powered signal. Let's look at magnetic core memory. The magnetic core memory became an important form of computer memory in 1950s and remained widely used for decades. It used tiny rings of magnetic materials called cores arranged in a grid, just like the way I've represented here. The cores did not need continuous power to preserve their magnetic state, and so this made the core memory non-volatile in practice. Although reading the state could disturb it and require the computer to write the value back. The Computer History Museum describes magnetic core memory as the first reliable high-speed random access memory for computers, and it was widely used into the 1970s. This was one of the most effective ways in the earliest times of trying to build a random access memory. We spoke about tapes, right? Magnetic memory in tapes or hard disks. That became useful for long-term storage. So it stores bits as a patterns of magnetization along the long strips. Tape is still used today for backups and archival storage. If you have heard of cold storages, most of them actually use magnetic tapes because it is cheap. It is per unit of capacity, it is inexpensive. It is efficient for sequential access. It is suitable for long-term offline storage, and it is resistant to some categories of online attacks because it can be disconnected. So let's say somebody was to hack into a data center, you know that you could just have this disconnected, and so data is going to be as safe as it can get. So that said and done, tape is not a good choice for fetching a random record very quickly, right? If you notice, let's say the required data is near the end of the tape, you have to move through so much of the tape before you can reach towards the end and then actually read that value. This is similar to the difference between searching for a song on a streaming service versus fast forwarding through an old cassette. And so hard disks were a very interesting invention. So hard disks improved random access for persistent storage. A hard disk contained rotating magnetic platters. The data is arranged into tracks and sectors. So let's look at this. There are tracks, right? This is a track, and then there is a sector. So if you know that your data is here, then you know which track to pick up and which sector to target. And so as long as your head can actually be brought, like the disk can turn towards this, you are now going to be able to move this mechanical piece anywhere around this and to read the value. I hope that makes sense. And so if I was to turn a machine off with a hard disk inside of it and turn it back on again, the magnetic properties of the platters isn't lost. It will just take probably a few seconds for the system to start up, and you can then copy over stuff from this persistent storage into your RAM, which is what your operating system would have done anyways. All right, so remember that to read data, the drive must rotate the platter to the right position, move the head to the correct track, read the magnetic pattern, and then return the data to the computer. And so this introduced several types of latencies. There is the seek time, which is the mechanical arm moving around, right? There is the rotational latency for your disk to move so that your arm can actually read that specific part. Then there is the transfer time, time needed to read this data and then pass it back to your computer in the 1 and 0 format. And then there is the controller and software overhead in itself. So if you notice, I just mentioned that the magnetism was to be converted to a ones and zeros to be handed back to your computer. Then there is the controller and software overhead. Your computer is not directly reading the magnetic properties of the disk, right? Your computer just instructs your hard disk to go and fetch the values stored at address so and so. Your hard disk figures out what the address corresponds to, which sector, which track to pick up, and then gets that data and then converts it to a binary format and then sends back that binary to your computer. If you notice, there is a bunch of calculation happening within the hard disk, and this is done by the controller, and there's going to be some software overhead for this as well. As discussed, hard disks offered much greater capacity than early memory technologies, although they were slower than RAM and contained moving parts, which is why the latencies. The architecture remains conceptually very simple. It is a large, persistent address space backed by magnetism and accessed through a mechanical mechanism. Electricity is used to move the head around and to turn the disk and to decode values stored, but you do not need electricity to be able to retain data in here. Magnetism is what powers it. Let's move on to what happened beyond magnetism and what made memory move out of this magnetic ecosystem. And here comes in the transistor. As electronics became smaller, computers moved from large discrete components to integrated circuits. A transistor can act like a controllable switch. You decide if it lets current flow or not, and therefore it could actually be emitting a 0 or a 1 depending upon the signal that you sent to it. Isn't this amazing? Like millions or billions of transistors can be combined to build things like logic gates, processors, memory cells, controllers, and all of the modern communication hardware that you and I today rely on. Modern RAM uses semiconductor circuits. The Intel 1103, which was introduced in 1970s, was an important early DRAM integrated circuit and marked the beginning of the decline of magnetic core memory. Although magnetic memory hasn't gone uh, completely, we all rely on some or the other format of magnetic memory in the data centers that you and I come to rely on. You may not have an account with a data center, but the fact that you use a bank, Google, Microsoft, all of these companies have and use some form of magnetic memory within their ecosystems. Let's talk about flash memory. Flash memory stores information using electrical charge trapped inside special transistor structures. It is non-volatile, which means electricity can be turned off and data would still be retained. It can retain data without continuous power. It is used in SSDs, USB drives, memory cards, smartphones, embedded devices, and even your cloud storage systems. Flash has no spinning platters, so it can be faster, smaller, and more resistant to mechanical shock than a hard disk. However, flash cells have a limited number of write cycles. Storage controllers deal with this using very different techniques. So for example, if I am saying flash cells can only be written to a finite number of times, it means data will eventually keep getting lost. Storage controllers are dealing with this in very different manners. There are error corrections, there is garbage collection, there is bad block management, and there is over provisioning. All of these are things you can look up. We have turned the limitations of these flash memory stores and made hacks so that you and I can reliably use 1 TB phones without having to worry about the fact that data will die. There is an internal management that looks at cells which are about to die or have been used more often, and then it is able to move data from those bad sectors to the correct ones. Isn't this amazing? An SSD is not simply RAM that remembers. It has different performance characteristics. Remember that the RAM that you and I use on our computers is very different from an SSD. SSD actually is able to retain stored, let's say, trapped electrons. And what do I mean with electrons being trapped? Here, these electrons cannot escape even with the power off. Once power is switched off, these electrons are stuck here. These chips allow us to send electrical signals to either trap electrons or to release them. If I want to release electrons, I can actually send in a signal to say, hey, let them go. I mean, we're literally holding electrons prisoners. So a very different way of thinking about how memory actually works without magnetism. As I mentioned, an SSD is definitely not just RAM that remembers. A lot of people, when SSDs came out, assumed that we now were just making large RAMs and we're putting them in SSDs, but that is not true, right? You already understand that RAM loses all of its data when electricity is turned off, which basically means an SSD cannot just be simple RAM. There is a very different technology behind SSDs. Yes, all of these are constructed using transistors and are built using the same silicon chips, but they have very different performance characteristics as well. In fact, what I was mentioning earlier, the fact that flash cells have finite number of writes is very important. Your SSD has an onboard chip which is doing a bunch of things. For example, wear leveling, which is to say, let me spread all of the writes so that no single block dies early. Then it does error correction so that if a cell drifts, let's say one of the cells actually became 1 to 0 or 0 to 1, there are error correction codes that can help your onboard chip detect that there is an error here and it can correct it. Then there is garbage collection, and then there is address translation. For every logical address that you send from the computer to the chip, it can map it to the physical address on the chip itself. It is very different than what a magnetic memory does. Now let's look at the storage hierarchy. Modern computers use a hierarchy because no single storage technology is ideal for every job. A useful rule is the closer storage is to the processor, the faster and more expensive it tends to be per byte. For example, if we look at CPU registers, these are memory built within CPU. Well, CPU caches are also built within CPUs. It also is divided into L1, L2, and L3. You could have a few MBs worth of CPU cache. It takes a few nanoseconds to be able to access CPU cache. RAM also tends to be in a few nanoseconds these days. It is fast, can support a few GBs. SSDs are persistent, they are fast, and they can be multi-terabytes. Hard disks are persistent because of magnetism, remember? They are cheap as compared to SSDs because they don't have a lot of transistors. And so you could literally have multiple terabytes worth of hard disks stacked together. And then there is the tape or the object archive. This is again the same magnetic tapes that we were talking about. These are really slow. They are the cheapest and they're effectively unlimited because you could have as many tapes as you want. The fact that every time a CPU needs data from these tapes, somebody has to go fetch them, load them up, and then get it read. That's where we are with the storage hierarchy. So let's take some examples. The operating system and applications constantly move data across this hierarchy that we just studied. A file could be stored in an SSD. The operating system reads it into RAM. Frequently used portions of this file could be moved into CPU cache. The processor operates on values in the register and results move back through the hierarchy. The operating system eventually writes durable changes to storage so that they can be persisted across restarts. And so that's why the phrase that my data is in my computer is probably not the best way to represent it. You should ideally ask, at which layer is the data currently represented? You have to make sure that data gets persisted to some durable storage before you call it quits and move on to other tasks. And so that brings us to the most important question that we started with. How do machines talk to each other? How do they understand what one machine is saying? For humans, there are a set of rules that are established. We call them languages. There is a grammar associated with that language. So let's try and understand how machines learned to talk. Storage and communication do solve related problems, right? Storage preserves representation across time, and communication moves a representation across space. In both the cases, we need a representation of the data, a physical medium to be able to transfer that data, a sender or a writer, and a receiver or a reader, and a way to detect errors. This is very important. Notice that a hard disk stores bits by changing magnetic states. A network cable transfers bits by changing electrical signals over time. A fiber optic cable transfers bits using patterns of light. A wireless connection transfers bits using radio signals. The medium changes, but the basic problem remains. How can one system create a signal that another system can reliably understand? To understand this, let's look at the ladder of distance. Physical distance creates new problems. Speaking works when two people are in the same room. It is not useful when the other person is hundreds of kilometers away. Humans have developed increasingly powerful communication systems. We came up with messengers, written letters, postal systems, flags and signal fires, optical semaphores, telegraphs, telephones, radio, television, fax, computer networks, and the internet. Each system reduced some combination of either the distance, delay, cost, human effort, or ambiguity. But each new method that we came up with introduced its own constraints. A messenger can carry rich information but is slow. A telegraph is fast over long distances but requires encoding the message. A telephone carries voice in real time but requires an active connection. A fax sends a representation of the document but traditionally takes time to scan and transmit this image. Computer networks combine many of these ideas in a way where communication can actually be asynchronous. They can actually happen over long distances. Cheap, you don't need 100% active connection. We'll discuss more about packet switching at a later point. But at the end of the day, we have done error correction, we do routing, we do flow control, and there is a very clear protocol that helps us understand what every in every bit of information that is received could actually mean. There is an application level meaning for every message that is received. Let's start with something really archaic and let's talk about the telegraph. The telegraph was one of the first major technologies to separate communication from physical movement. A message no longer had to be carried as an object. It could be converted into electrical signals and sent through a wire. Morse code represented letters as a pattern of short and long signals. For example, a short signal, a long signal, a pause. The receiver needed to know the encoding rules. Without knowledge of Morse code, the electrical pulses would not have any meaning. This is exactly what happens in computer communications as well. Bits can travel across a wire, but they are not automatically a message. The sender and receiver need to agree on a few things. What are those? The timing, the encoding, the boundaries, the meaning, the error handling. Let's talk about a telephone. The telephone allowed people to communicate using voice over electrical networks. Unlike the telegraph, it did not require the sender to manually translate every letter into a code. The voice itself was transformed into a signal. However, telephone networks still required complex coordination. How should a call be established? How should the network find the recipient? What happens when the line is busy? How are multiple conversations separated? How should the connection be terminated? The telephone introduced the idea that communication is not just about sending content. It also involves managing a session. Modern apps still need this. When you join a video call, the system must coordinate. What all does it need to coordinate? The identity. A connection setup needs to be done. Media negotiation has to happen. Packets, delivery mechanism has to be established. Encryption needs to be established. Disconnection and reconnection needs to be thought of. And then there came fax. Fax machines converted an image into a sequence of signals, transmitted those signals, and reconstructed the image at the destination. If you can see here, the document scanned into a grid, sent as signals on the phone line, and then reconstructed into a document all over again. Modern apps also do this. The output is just a web page or a JSON response or a database row. The ideas have now started moving in the direction where we want to understand it. That said, let's get to what is a protocol. A protocol is an agreed set of rules. That is it. That's the simplest definition. A protocol tells the participants how to begin, what messages will look like, how messages are ordered, and how to identify the sender and the receiver, how to detect errors, how to respond, and how to finish. For example, if you were to write a letter, you are expected to write a from address and a to address. Without that, the letter cannot be delivered by the postal system. So there is a protocol that you need to follow to be able to send letters over postal networks. Hope that makes sense. In fact, a conversation between humans also has protocols. For example, one person says hello, the other person responds. Someone asks a question, the other person answers. The conversation can end once the other person walks away or simply says, thank you, bye-bye. These rules are flexible in human language, but machines need much more precise instructions. And they are not intelligent creatures. Humans are different. Let's consider a simple protocol for ordering chai. In case the client orders for chai, the server, here the server is the chai stall server, can say, okay, what type? And so the client can say, hey, I want masala chai. And so the server can then ask, how many do you want? Quantity 1. All right, it's ready. Thank you. And transaction is over. If you notice, while this in itself could happen in multiple ways, there is still some protocol that humans also follow. So let's say instead of two humans, there is a client and there is a server. There is no clearly established protocol. There is a chance that one computer would communicate in plain text and the other computer may be expecting a JSON, right? In which case, even if the client requests for tea and sends a message of order tea, the server is not going to be able to understand it. It was expecting a JSON, right? I hope that makes sense. So if both are looking at different protocols, communication cannot happen. Both the machines which are looking to have a conversation need to be on the same protocol. There's nothing wrong with any of these computers. The connection exists. It's just the fact that there is no shared agreement of which rules to use and follow, and that in itself is enough to stop everything. Therefore, protocols are also contracts. Unlike in the case of humans, where a syntax and the language is sufficient and you can figure it out on the fly, protocols are like contracts when it comes to computers. Protocol is similar to a contract between systems. It defines an interface that lets independently built components work together. So a computer built by Apple and a computer built by Microsoft could communicate with each other over a shared protocol if both of them were following the same rules. For example, an HTTP request can contain method, URL path, headers, optional body, a response status, some response headers, and a response body. If you were to send a HTTP request, these are the things that you can send. And if the other party understands the same protocol, it would mean the client can then understand whatever you communicate with it. Which is why a browser and a web server written by very different companies. Let's say you're using an Nginx server and there is a browser built by Mozilla. They can communicate with each other because they follow a shared protocol, that is HTTP. This is one of the deepest ideas in computing. Standardized communication allowed independent systems to cooperate. And this is how the internet eventually became a big thing. Why is one protocol not enough? Well, communication has multiple problems. How do you convert these bits into electricity? How do you group them into frames? How do you identify other computers on the same network? How do you identify computers on cross networks? How do you notice when a few bits go missing? How do you denote these requests themselves? And how do you ensure data is only accessible by the correct parties? If you look at it, you could definitely have a giant protocol which could define all of these things as a set of rules, but it would make systems difficult to design and evolve. Instead, computer networks started using layers. Each layer solves a particular class of problem and relies on the layer below it. Let's look at this. Because we stacked these, let's first look at the application layer. An application layer, in fact, is, let's say, your browser. Your browser never thinks about if my data is flowing through as signals on a copper cable or as light inside a fiber. After application, there is the security layer, which is where you figure out how would you protect data between the receiver and the sender. Then there is the transport layer. How do two programs exchange data? Then there is an internet layer, which is where you decide how does data cross over from one network to the other. Then there is the link layer. This is where you figure out how do local devices talk. And then there is the physical layer, which is where signals are actually sent. These layers are conceptual. Real implementations may combine responsibilities, and different models use different names. The main benefit is separation of concerns. An application such as a browser does not need to know how a bit becomes light inside of a fiber cable. It asks for a network connection through operating system interfaces. The lower layers handle the physical details. Hope this makes sense. Let's take a step back and go back into circuit switching, which is how traditional telephone networks used to work. When a call was established, the network would reserve a path or capacity for the duration of the call. These lines are now busy for the duration of the call, and nobody else can use these lines. These are dedicated lines. The advantage of this is definitely, predictable communication. There is a continuous connection and it is suitable for real-time voice. The disadvantage here is that these resources can remain reserved during silence as well. A fixed path obviously is less flexible. Let's say there is a network failure, it can interrupt the call itself. Capacity is not efficiently shared for bursty traffic. And finally, that brings us to packet switching. Packet switching divides data into smaller units called packets. Each packet contains a part of the message, the address of the recipient, some metadata, and occasionally it also contains some error correction or error detection information. Packets can share network links with packets from other conversations. A simplified example. So if I was to switch a message like hello computer, it could actually be split into two different packets. Let's say hello and computer. You have the to address and the from address. On both of them independently, there is a packet detail. There is some error correction code that the packets can contain, and there is a sequence number for both of them. So once received, the recipient can then connect them together to realize the final message as hello computer. And because, and this is the best thing about packet switching, and because networks that use packet switching do not require a dedicated channel, messages can actually share the same path with other messages not related to each other as well. Like it's the same wires shared by everyone from one moment to another. Message 1 could have gone via one path, and message 2 can go via another path. As long as both of them are received by computer 2, it can be stitched together because they are following our protocol. The packets may travel through different paths and may arrive out of order. The receiver needs a protocol to identify packets, reassemble them, detect missing packets, request retransmission where necessary, and then deliver the complete message as a stream to the application. Packet switching was central to the development of wide area computer networks. ARPANET became a major early packet switched network, and its interface message processors evolved into concepts similar to modern routers. That brings us to the network of networks. Connecting two computers is not enough. Imagine two networks where network A uses one type of packet format and network B uses another. Network C may be using radio. Network D could be using satellite links. If each network works internally, can a computer on network A communicate with a computer on network B? Not automatically, right? Because networks may disagree about the address format, the packet size, error handling, routing, delivery guarantees, and connection management. The next challenge was to create a network of networks, and this is where internetworking protocols became important. The word internet comes from the idea of interconnected networks. Let's talk a bit more about this. TCP/IP is not one single protocol in the everyday sense. It's a family of protocols with two particularly important members. IP, which is called the Internet Protocol, handles addressing and forwarding packets between networks. TCP is Transmission Control Protocol that provides a reliable ordered stream of bytes on top of an unreliable packet network. So Internet Protocol actually does not guarantee ordered flow of packets, but TCP, which is built on top of IP, makes sure that the data that you receive if you are listening to this protocol is coming in a reliable ordered stream of bytes. IP makes a best effort to deliver packets. Packets may be delayed, duplicated, lost, delivered out of order, and so on. TCP adds mechanisms such as sequence numbers, acknowledgements, retransmission, flow control, congestion control, and connection establishments. You see, these are complementary protocols. And as we discussed, you don't want to make one large complicated protocol. You want to have separation of concerns where one protocol is doing just one thing. IP will make sure that all the packets are attempted to be delivered to the right computer. There can be delays, duplication, there can be lost packets, and they could have arrived out of order. TCP makes sure it checks all the incoming packets and then sequences them, sends back acknowledgements, requests for retransmissions where there is a lost packet. It can also do flow control, which is to say, control the speed at which packets can be received or sent. It can do congestion control along similar lines, and it can do connections setup as well. Hence, TCP is giving you a reliable ordered stream of bytes. There is no guarantee that each of your messages arrived exactly once. It could be received multiple times. It doesn't matter. TCP will take one instance of every message and stitch them together. If a message is missing, it will re-request for that. All of that is taken care of by TCP, so your browser doesn't have to worry about any of this. If you notice, every layer is wrapping the one above it. HTTP data, which is your actual request, is wrapped inside of a TCP header, which is sent with an IP header inside the Ethernet header, right? So while you are sending, each layer adds its own header, and when you are receiving, each layer will strip its layer from the top. Which is to say, when a browser gets a TCP response, it will strip off the TCP headers and then look at the HTTP content of the message. Nobody opens a layer that isn't theirs, if that makes sense. And this is the beauty of encapsulation. Here is a simplified way. Application messages are divided by TCP into a byte stream so that it can track delivery. IP adds source and destination addresses. The link layer sends frames across one local network, and the physical layer actually sends these signals across the network. At the destination, the process happens in reverse, and this is called encapsulation. Each layer adds its own header around the data from the layer above. Now that we have some basic understanding of TCP/IP, let's try and look at the adoption of TCP/IP. The development of TCP/IP involved work by Vint and Robert, a few other researchers. Cerf and Kahn published a foundational paper on protocol design for interconnecting packet networks in 1974. In 1983, ARPANET adopted TCP/IP, which was a major milestone in the development of the modern Internet. The significance was not merely that one network became faster. The larger achievement was that different networks could cooperate using common rules, which is why you have to remember the Internet is not the web. These terms are often used interchangeably, but they are different. The Internet is a global network infrastructure and protocol ecosystem. The web is an application system built on top of the Internet. Web uses technologies such as HTTP, URLs, HTML, CSS, JavaScript, browsers, web servers, right? When you open a website, the browser interprets a URL. DNS helps find the server's IP address. The browser establishes a connection. It sends the HTTP request. The server processes that request and sends back an HTTP response, and then the browser renders the content. The actual bytes travel through multiple layers of protocols, as we saw earlier. The application sees a request and a response. The network sees packets. The physical medium sees electrical, optical, or radio signals. All three descriptions refer to the same communication event at different layers. One of the most important things to understand is the fact that the same message at different layers is a very different representation. What looks like get/products as an HTTP request could actually be just some packets of information for the network layer and then just ones and zeros for the cable layer. You have to understand, very importantly, that depending upon the layer at which you're operating, the representation of the same data could be different. Once you understand this, we can now talk about the topmost layer at the application layer, what happens when you open a website in your browser. Let's follow a simple example. When you enter https://example.com, the browser parses this address. It realizes there is a scheme HTTPS domain or the host is example.com and the path is slash. The browser sends this request to the DNS directory. What is the DNS? Well, exactly the way humans prefer names, networks use IP addresses. DNS, which is short form for domain name system. It maps names such as example.com to the IP address the domain name belongs to. This is similar to using a contact name on your phone instead of memorizing a phone number. The DNS response may be cached in several places. It could have been cached by a browser, it could be cached at the OS level, it could be cached at a resolver, or it could be cached at your internet service provider level. Once DNS resolves the name, the device tries to find a route to the destination device. So it may send traffic to a home router through an ISP across regional networks through backbone providers into a cloud provider. Once the route to the destination host is found, you try to establish a secure connection. For HTTPS, the browser and the server negotiate encryption using TLS. Once a secure connection is established, your browser will send the request using this established connection. This request may travel through proxies, CDNs, load balancers, API gateways, and whatnot. But once it is received by the host, it can respond with either HTML or JSON or plain text, depending upon what you requested for. The response is received by the browser and reconstructed into a page that it can show to you. Once the browser receives these bytes, it interprets them according to the relevant protocols and formats. It may parse HTML, download CSS, execute JavaScript, fetch API data, decode images, and then renders pixels. The page you see is the final result of multiple layers of representation, storage, processing, and communication. It is very important for us to understand that an application sits on many abstractions. When you write an API endpoint, you may write something as simple as some TypeScript code written here, but it depends on so many things: CPU instructions, memory allocation, operating system schedules, sockets, TCP, IP, Ethernet, DNS, TLS, HTTP, database protocol, storage and flash controllers. Do you realize this is why abstraction is valuable? Because it lets us build complex applications without manually controlling every transistor. I think it's worth keeping. Remember, storage is preservation of data across time. RAM is just the working area. Persistent storage preserves data across restarts and power losses. Different storage technologies represent bits using different physical mechanisms. We discussed holes in papers, magnetic orientation, electrical charge, optical modes, semiconductor state, right? Communication is moving data across space. It could be moved using air, wire, fiber, radio, satellite, storage media that is physically carried between locations. You could literally just collect data into a pen drive and travel with it to the recipient and then download the data there. That in itself is a mode of communication. Protocols create shared expectations. A protocol defines how systems communicate. It answers questions such as what is the message format, who speaks first, how do we identify the destination, how do we detect errors, what happens when a message is lost, how do we know the conversation is complete. Without shared protocols, independently built systems cannot reliably cooperate. 4. Layers manage complexity. The network stack divides a difficult problem into smaller problems. Application does not need to understand radio modulation. Likewise, the physical layer does not need to understand the meaning of a shopping cart request. Each layer has a responsibility and an interface with neighboring layers. That design is what allows the same application protocol to work over different physical networks. For example, your browser works the same irrespective of if you're connected via an Ethernet cable or if you're connected over Wi-Fi. Lastly, remember that modern computing is communication at scale. A modern application is rarely a single program running in isolation. It is usually a collection of components communicating: browser to server, server to API, API to database, service to queue, worker to object storage, application to payment provider, model gateway to inference service. The same basic problems appear repeatedly. How do two independent components exchange information correctly despite distance, delay, failure, and different implementations? That is the problem protocols help solve. The story of computing is often told as a story of faster processors. That is only a part of it. There is also the story of information, how to represent information, how to store it, how to preserve it, how to move it, how to interpret it, how to protect it, and then how to coordinate systems that do not know each other in order to be able to exchange information. Humans began with sounds, gestures, and symbols. We created writing to preserve communication across time. We created telegraphs and telephones to communicate across distances, and we created computers to process information. Then we connected computers so that they could communicate with each other. Today, when you send a message or open a website, you are participating in the result of that entire history. A single action may involve bits in memory, persistent data on storage, encoded signals, packets, routers, protocol layers, servers, databases, applications, and the actual human meaning of the message itself. The next time you build a website, call an API, or send a database query, remember that the abstraction is hiding a long chain of ideas. At the bottom, the machine is still switching physical states between 0 to 1. At the top, two humans are trying to understand each other, and everything in between exists to make that communication reliable.